In the first part of UAV networks, we had covered the basics of UAV networks. We started with the physics behind these UAV networks and the basic communication and the topologies that are used while forming these networks. So, currently we are going to cover even further in depth of these networks in this particular part, the second part of UAV networks. So, what we are talking about are the two different topologies of UAV networks, the star topology and the mesh topology. So, here is a comparison of these two different forms of topology. We have already seen the pictures of these different topologies, the star topology and the mesh topology. So, what we have is point to point connectivity in the star topology, whereas we have multi point to multi point connectivity between the different nodes in the case of mesh topology. So, we have central control point that is present in a star topology, whereas in the case of mesh networks, mesh topology, we have infrastructure based which may have a control center, or if there is ad hoc part of the network that we are talking about, it does not have any centralized control center. So, it is, as I said earlier as part of the previous part of the lecture on UAV networks, either the infrastructure based communication may be used, or an ad hoc network communication may be used for these networks. So, infrastructure based or infrastructure based and ad hoc. Then we have the ad hoc, the star networks are not much self configuring, whereas in the case of mesh networks, because of the overall reliability, increase in the reliability of the different nodes, in the presence of faults as well, these mesh networks can be self configuring, self healing in fact, and self managing overall. So, there are other differences between these different types of topologies. I am not going to go through, but it is in front of you for you to go through and be able to appreciate. There are different features of UAV topologies. These UAV topologies are very much prone to different types of disruptions. In fact, these are prone to different types of delays as well. The disruptions could be due to the mobility of the UAVs with respect to each other. The power transmission, there might be failure in power transmission inside a particular node, or maybe that the inter UAV distances might have increased to the extent that they are not able to communicate with each other, and there could be other environmental or extraneous noise that might also lead to disruption of communication between the different nodes in these networks. Delays could be due to poor link quality, which is quite common in these networks, and due to end to end path not being available at all points in time. There are different categories of UAV networks. UAV networks can be categorized in terms of internet delivery, the sensing, or kind of attacks. So, we are going to go through each of them in a short while. So, in terms of internet delivery, there are different applications of disaster communication. So, communication or networking in the case of disasters, oil exploration, remote health monitoring, and so on. The topologies that can be used are the star topology or the mesh topology, and both infrastructure based communication and where the base station is in the sky, or even the ad hoc form of communication might also be used for internet delivery, but typically it is the infrastructure based communication with the base station in the sky that is the kind of topology that is used for internet delivery. Then there is centralized position control in the case of UAV networks for internet delivery, and the server. So here basically what we have is the client or a server. The server basically communicates the routes between the different nodes, the communication that occurs between the different nodes, and they can these nodes can act as different servers, and the routing is made through the servers. In terms of sensing, applications such as reconnaissance, performing reconnaissance missions, different search operations, detecting forest fires, tracking of wild animals, etc. For this basically you also need, in addition to the UAVs to communicate with one another, you also need them to be sensor enabled. They can sense different things, and again the type of topology that is used here is the mesh topology, and the kind of control is the centralized control, and the kind of routing that is used is either a centralized routing, or routing that is typically adopted in the case of mesh networks. In terms of the attack, which is the third category of UAV networks, these type of UAV networks can be used for wartime scenarios, where it is required to have multiple UAVs perform some kind of an attack for war scenarios. So the type of network that is used could be infrastructure based or infrastructure less, that means an ad hoc network, or the topology that is used is a mesh topology, and the routing consequently, the kind of routing that is used is the mesh routing. The ad hoc networks that are formed using these UAVs or these flying devices, they can have different structures. So here is a typical structure of ad hoc networks formed using these aerial devices or the flying devices, which is called this type of structure or this type of network topologies are called FANETS. Flying ad hoc networks is the full form of FANETS. And as you can see over here, this is the vertical profile of these the FANETS. So as we can see from this particular figure, what we have are different UAVs flying in different layers, in different levels. So what we have is one UAV in one altitude, these three UAVs flying in the same plane in a different altitude, and these three UAVs in another plane higher up in another altitude. So we have together a flying ad hoc network, and so what could happen is these UAVs in a particular plane, they should be able to communicate with each other, and the same thing happens in the different other layers as well, and also between these different layers they should be able to communicate with each other. There are different features of these flying ad hoc networks. These features are basically dependent on the type of communication that is taking place, and this is something that I have already spoken a short while back. So with the ground station, basically these UAVs in the different planes, they can connect with the ground station in this manner, and so between in a particular layer, these UAVs can also talk to each other, and the UAVs can also talk to each other across different planes, like in this particular example. So this UAV in this plane is able to talk to this particular UAV in another plane, and so on. So across different planes also these UAVs can perform different types of communication. So in a FANET we have interplane communication, that means across planes interplane communication. We have intraplane communication, that means within a particular plane the different UAVs that are there, they should be able to communicate with each other, and we also have communication from the ground station to the different UAVs in different planes. So FANET, so ground station communication, ground sensor communication, and VANET communication. VANET communication means that within so there is a vehicular ad hoc network on the ground, and from that vehicular network the different nodes should be able to, in that particular vehicular network, not only they should be able to communicate with one another, the different vehicles should be able to communicate with one another, but also they should be able to communicate with the UAVs which are flying. So this is the overall idea of formation of FANETs. So FANETs do compare with ad hoc networks. In fact, FANETs and ad hoc networks, they can be integrated together as well. So here is an example. The first figure what we see is we have different A to A, that means air to air links like this, then we have air to ground links like this, and then we have ground to ground links like this. So this is one type of architecture of these flying ad hoc networks, and this is another architecture of this is more like a mesh like architecture over here, and this is more like a star kind of architecture that is used here, where the ground devices, they are able to communicate through direct link with the centralized coordinator in this particular in this particular case. In this particular layer, this is acting like the coordinator in this particular layer, which can help coordinate the communication between these different nodes, the UAV nodes in this in this plane. So, distributed gateway selection is a very important problem. There is so if we look at a UAV network like this, if we are talking about this, so what is very important is to select the gateways. So, the main communication requirements of UAV networks are sending back the sensor data to the ground, receiving the control commands, cooperative trajectory planning, and dynamic task assignment, and the number of UAV ground remote connections should be controlled to avoid interference. The less number of such kind of connections between the UAVs and the ground, that means A to G kind of communication, the lesser the number of such kind of communication or the connections we have, the lesser these networks are prone to interference. So, the reduced nodes in these UAV networks should act as gateways to allow communication between all UAVs on the ground, all UAVs and the ground, sorry. So, these UAV networks they are formed, they are deployed in such a way that they have to cover a particular area. So, if we look at the figure in front of us, what we see is a figure like in the case of the previous slide. So, here we have different UAVs in a particular plane, and these UAVs together they will have to accomplish a particular mission, maybe a reconnaissance or something like that, where they have to go and cover a particular area. So, that particular area could be divided into different sub areas as shown over here. So, what we have, this is one sub area, this is another sub area, this is another sub area, and so on and so forth. So, this entire UAV area is divided into different sub areas. So, these sub areas collectively cover the entire communication area. The size of a sub area to be controlled is to be controlled and adjusted dynamically, because the network topology is also quite likely to change quite fast in this network. So, it is very important not to have a fixed zone, but to change these zones or these sub areas dynamically and control them. So, these adjustments are based on UAV interconnections and derived metrics. The derived metrics are optimized for several iterations till optimum state is achieved. So, how is the gateway selected? The gateway selection is initiated by the selection of the most stable node in the sub area. So, we have different sub areas as shown over here. So, we have different sub areas, and this is how it is shown over here. So, we have sub area 1, sub area 2, and their projections on the plane. So, we have these projections, we have sub area 1, 2, 3, 4, 5, and so on and so forth. And in each sub area, what happens is the most stable node in that particular sub area is identified and selected, and that particular node is identified as the gateway node, and consecutively the partition parameters are optimized according to the particular topology, and each UAV acquires the information of all UAVs within its 2-hop neighbors. This is the layered structure of deployment of these UAV networks or the FANETS. So, what we have over here are these different nodes that are deployed in different planes. So, as we can see over here, these nodes which are marked with red colored circles, they are identified as the gateway nodes, and these gateway nodes, they can help these gateway nodes in the different planes, they can help connect with the other gateway nodes in the different other planes. So, the gateways from each layer communicate to forward information between the layers as well as the ground control, and that will increase the delay between the ground control and the higher layers, and this type of architecture is not very suitable for time critical applications, because these basically increase the overall delay of the network, although there is greater coverage and improved connectivity, but it is at the cost of increased latency as well. So, when we talk about VANETS, we are talking about vehicles and different nodes, the human beings or whatever carrying different mobile phones. So, we have VANETS, MANETS on the ground. So, then if we are talking about VANETS, these VANETS can communicate, VANET node can communicate with a UAV node, and so we can have different links. So, not only we have V2V links as in the case of VANETS, but also we can have A2V links, that means air to vehicle links. So, we have air to vehicle links. So, we have we have ground control, we have vehicle to vehicle communication on the ground, and then with the multi UAVs on the air, there is control, there is scheduling, there is different other requests, sensing, navigation, etc., etc., different types of information exchanges that can go on between the different nodes in the air and from the air to the ground and on the ground as well. So, these nodes, they are moving, their trajectories have to be controlled, and if we are talking about a swarm of these UAVs, then their control has to be different depending on the type of swarming behavior that is desired. UAVs with Q occupancy above a particular threshold, they are likely to experience collision, resulting in communication delay. The control station instructs the UAVs to change the centers of the trajectories, and the command is given based on the traffic at the busy communication link. So, these are some of the very fundamental things about communication, about trajectory control in the case of these networks. So, as we can see over here, in this particular case, we have different UAVs, a planar view of these UAVs deployed. So, as we can see, these are basically these figures, they basically show that how many packets can be queued at the different interfaces of these UAVs when a structure like this, a topology like this is deployed. So, what we can see over here is through this interface, the buffer occupancy of this interface is 90. So, if the buffer occupancy of this interface is 90, then what can be done is this particular UAV which has a lesser buffer occupancy, this can move from this particular position and come closer to this particular UAV and can help this particular UAV which already has its buffer capacity full to be able to communicate with the rest of the nodes in this network, and that will improve the overall throughput because lesser number of packets are going to be deployed. So, what we can see over here is this particular UAV, it moves about 20 meters or so. This is just an example, of course, about 20 meters or so it moves in towards the direction of this particular UAV, so that after movement, after moving over here, this particular UAV can help this overloaded UAV with increased buffer occupancy to be able to route packets from this UAV to the other nodes. This is just an example, a comparison of how this is taken from this particular reference that is given over here in this slide. So, what we see is how through trajectory control, how the throughput can be increased in the case of UAV networks. So, in terms of comparison of the uniform UAV deployment and the proposed UAV deployment, we see that overall the performance of the proposed UAV deployment is improved compared to the uniform UAV deployment. So, this is proposed means proposed by the authors of this paper. So, this is what they proposed, and they have shown that the trajectory control, the way it is shown, helps one to achieve improved throughput, improved efficiency compared to having a pure uniform UAV deployment in a particular region. And again, these are the references that can be used to understand these concepts that we have covered in a short while in detail. Thank you.